Hello and welcome to this first lecture in astronomy. This is over chapters 1 and 2, and we'll start with chapter 1 and get started here. So chapter 1 is really just an overview of astronomy and what we study in this field. We'll look at some pretty pictures and talk about various things. Distant galaxies. This is a Hubble Space Telescope picture. Hubble's been up since 1990, been up there a long time, 27, 28 years. And its replacement, the James Webb Space Telescope, is due up very soon at the time of this recording in 2018. So these are two interacting galaxies. They each contain hundreds of billions of stars. And they look like they're colliding, but there's actually a lot of space in between the stars. Between the sun and our nearest star to us, there's 4 light years, 4.25 to be exact. And so there's lots of space. So what we're really seeing here is a merging of two galaxies, and the gravity inside of each one kind of tugs and pulls on each one and distorts them a little bit. Here's a great picture of Mars, courtesy of NASA. I had 20 great years with NASA as an astronomer, mission science team member, and public outreach specialist. What we see on Mars here is a valley called Mariner Valley, or Valles Marineris. It's first seen in the 70s by the Mariner spacecraft. And this is a rift valley that's carved out that would put the Grand Canyon to shame. This thing is as long as the United States is wide. So the Grand Canyon would just be some tiny little bitty chasm inside of this thing. Remarkable. Mars also has the largest volcano, which puts Mount Everest to shame. Here is the remnants of a stellar explosion, a supernova. This is Supernova 1054, seen by the Chinese. And they notated this in documents. And this is the result of 1,000 years of expansion of a star blowing itself to pieces, exploding from within. And so we have not only hydrogen and helium, which are the building blocks for stars, we have carbon, nitrogen, and things like iron in your blood, and the oxygen we breathe, and the calcium in our bones. That all gets made up in exploding stars. And iron is as far as we can fuse elements into in a star, and then it goes bang and blows up. Can't go any further. Here's one of my most favorite objects to study, and I spent a lot of time studying this. This is the Orion Nebula. This is a winter constellation, the constellation of Orion. And in Orion, we'll see a picture here in a minute. I'll show you where this nebula is located at. But right in the very middle here, you can see a few stars clustered together. And me and my college advisor of 20 years, we studied some eclipsing binary stars in that cluster. These are stars that are paired up together and they go around and they eclipse, kind of like the total solar eclipse we just saw in August of 2017. And studying those kind of stars was my main field. And you can get masses and diameters and temperatures of stars, and that's the main way we have of getting masses for stars. And but it was very difficult to study because we like to have a very dark, empty background to be able to get the brightnesses of these stars, and we don't have that here. We have all this gas and dust floating around, and that made it very challenging, which made it very exciting to study because it's quite a challenge. And so the Orion Nebula is about 1,400 light years away. So when you look up in the winter sky and you look at Orion and look at this nebula, you're looking at it as it appeared 600-700 years after the birth of Christ. Here's the Hubble Space Telescope, named after Edwin P. Hubble, who did work on galaxies and the expansion of the universe and tried to determine how old the universe was and how fast it was expanding. And a keynote for myself personally, I live in Springfield, Missouri, right along Interstate I-44 that runs between Tulsa, Oklahoma and St. Louis, Missouri. And Edwin Hubble was born in Marshfield, Missouri, which is 25 miles up the interstate. And there's a 10-mile stretch of the interstate called the Edwin P. Hubble Memorial Highway. And on the town square of this small town named Marshfield, they have a history museum for Edwin P. Hubble, and they have a one-third scale model made of aluminum and stainless steel of the Hubble Space Telescope. And there's even an elementary school there named after him. So here's our home base, the Earth, from a geostationary orbit point of view, 22,000 miles high. This is where we park our weather satellites and communication satellites, because at that distance, you're about the same distance as the circumference of the Earth, and your orbit around the Earth is 24 hours. So you're rotating at the same speed the Earth is rotating. So in effect, that satellite stays over the same point of the Earth, which is really good for communications, GPS, for weather satellites to monitor hurricanes and storms. And so this image is courtesy of the Goddard Space Flight Center, NOAA, which runs the United States, the National Weather Service, and United States Geological Survey. Here's a scale diagram of between the Earth and the Moon. You can see their relative sizes and distances. And this is not the scale, but this shows kind of our stellar solar system, what we have near us. We have the Sun, again, not the scale, but you can kind of see and somewhat a little bit to scale. Mercury, here's Venus, our Earth. Mars is a little bit smaller. And here's the big one, Jupiter. Saturn with its rings. We just finished up a enormously fantastic mission to Saturn for almost 20 years with the Cassini mission. Studied it very well. Uranus, Neptune. And then you'll notice Pluto's not there. Pluto's down here with Ceres, which is was the biggest asteroid. Now it's so big we call it a dwarf planet. And in recent times we have found out that this dwarf planet Ceres actually has activity on it, geological activity. Has ice melting and refreezing on it, and it's coming from within Ceres. We flown past Pluto in 2015 with the New Horizons mission and found that Pluto is fantastically geologically active, and so is its moon Charon, and it has 4 other tiny moons. So in 2005, the International Astronomical Union, better known as the IAU, took a last-minute, last-day vote on a 17-day-long conference to demote Pluto and make it a dwarf planet instead of a planet. They had never defined what a planet was, so they defined it. After they defined it, they said Pluto's no longer a planet. I can tell you that more recently, the IAU had a meeting in Hawaii recently, and the lead investigator of the New Horizons Pluto mission, Dr. Alan Stern, a friend of mine on Facebook, refused to go there to give results of the mission because of their decision. Not one single planetary scientist was among those who voted to demote Pluto. It's kind of like a welder or an architect going into someone's kitchen and saying, I'm going to make a chef salad, I'm going to teach you how to do it. That's not their expertise, that's the chef's expertise. Well, demoting Pluto was not the expertise of these few scientists left remaining. And so we have some dwarf planets there. Here is what may be what our Milky Way galaxy looks like, a spiral galaxy, 200 billion stars. Um, we think our spiral galaxy has a bar going through the middle of it, and then these spiral arms come off that bar, which is very neat. And these spiral arms are blue and have gas and dust. You can see the dark lanes there are dust. Gas and dust are the building blocks for star formation. The Milky Way over the California desert there, beautiful sight. Again, you can really see the dust embedded within the gas. If that dust was not inside this arm of the Milky Way galaxy that we're in, and we're 2/3 away from the middle of it in the armband, you could actually read a book at night just by the starlight in the sky. Fascinating. We have star clusters. A lot of them are globular star clusters, which are very old stars, 10, 12 billion year old stars. This one, and a lot of these like this, are called M9. It comes from a catalog called the Messier catalog. It has about 130 objects in it. Some people like to have, there's a very short window of time frame during the year where people have Messier marathons with their telescopes, and they get binoculars and telescopes out and they try to find every single one of these Messier objects in one very long night. And there's an organization that will give you the Pell Pen for a certificate for doing so. And so this globular cluster M9 has 250,000 stars in it and 25,000 light years away. This picture from the Hubble Space Telescope, and a lot of these are around our galaxy in the halo. We have neighborhood galaxies. We are in a group of galaxies near us called the local group. And among these are some small irregular galaxies called the Large and Small Magellanic Clouds. You have to go to the southern hemisphere to see these. And so this is an image of the Large and Small Magellanic Cloud as seen from this Atacama Large Millimeter Submillimeter Array, or in northern Chile, a radio telescope array. And radio telescopes at a certain wavelength of 21 centimeters can see molecular cold hydrogen in these gas clouds. And so here is our next door neighbor, and it's a really big brother to us, the Andromeda Galaxy. Another Messier object, M31 is its designation. And it's a massive spiral galaxy, and you can see it's tipped at a 45-degree angle. Very bright core there that has at least 2 black holes in it, and you see that prominent dust going through the spiral galaxy and some other little galaxies around it too. And our galaxy, the Milky Way, and the Andromeda Galaxy are coming together. It won't happen for a number of billions of years, but they are going to collide someday. And further out, we have clusters of galaxies. And so we're looking at a cluster of galaxies called the Fornax cluster, which is 60 million light years away. So the Andromeda Galaxy is 2.5 million light years away. So when you look at that, you're looking back 2.5 million years in time. Well, with this picture, courtesy of the European Space Organization, this image of galaxies is 60 million light years away. And so you're looking at how these galaxies looked right after the dinosaurs went extinct. It has taken 60 million years for that light to reach us. Fascinating. And so if we were to take the whole realm of the universe, and the whole time we've been around, which is estimated to be about 13.8 billion years, the universe, the known visible universe has been around, and you scratch that into a calendar year, this is what would happen. January 1st, you would have the Big Bang going on. And then in May, the Milky Way galaxy forms. In September, 4.5 billion years ago, the solar system forms. And then by November, complex life starts to appear on Earth. It wasn't until Christmas Day, on the 25th of December, that the dinosaurs appeared. And the next day, mammals appeared. On the 30th, the dinosaurs became extinct 65 million years ago, and then it wasn't until the last few minutes of the last day, the 31st of December, New Year's Eve, that the first humans appeared. So human lifespans infinitely small compared to the lifespan of the universe. Even the dinosaurs being around is only a week out of 52 weeks of the universe being known. And here's a beautiful picture of the Milky Way along with the Magellanic Clouds seen from Atacama Desert in Chile. A place I would love to go visit. The closest I have been to the southern hemisphere was southern Arizona at Kitt Peak National Observatory. And so this is a very dark mountaintop with lots of telescopes and very beautiful stuff. Actually, the southern hemisphere sky is much more beautiful and more full of beautiful things to look at than we have in the northern hemisphere even. Moving on to chapter 2, we're going to take a look at the sky around us. And so we have some points in the sky, and we'll show you a model of this here in a minute. The point directly above you, no matter where you are on the Earth, the point directly above you is called the zenith. And 90 degrees down from that, where the land meets the sky, is the horizon, wherever you are. And so in science, we like to make models of items and theories. And a model is simply a simplified form of a big complex idea. So the complex idea is the big sky, everything in the universe. So what we do is we have the Earth in the middle of this model, and if you see this in real life, it would be a clear plastic sphere around the Earth. And we take the North Pole of the Earth and extend it straight out to the model, the celestial sphere, and we get the North Celestial Pole. Again, wherever you are on the Earth, straight up is your zenith, and straight out where the sky meets the ground is your horizon. And Earth's equator can be stretched out to become the celestial equator. And we talk about stars and planets being above or below that area of the celestial equator, north or south. And so we rotate on the Earth. We rotate on our axis every 24 hours, and that, if you were to take a long exposure at the sky, that gives you a look at how the motion of the sky appears to us to go in a circle. And so while the North Pole has a star right next to it, Polaris, the pole star for now, the South Pole doesn't have a star next to it, but you can see here this image, probably again from Chile. This is from the European Space Organization, the South Celestial Pole, and the stars going around it. And that's probably a couple hours of rotation there. So the stars would look differently at different altitudes. If you're at the North Pole, you would see the stars circle in a certain way. If you're at the equator, you would see them circling at the horizon. And you can tell, if you're a Boy Scout, this is the Boy Scout way of determining where you are on the Earth latitude-wise, how high above the equator you are, however many degrees above the horizon the North Pole star is, Polaris, in the constellation of Ursa Minor, the Little Bear. That's your latitude on the Earth. So I'm in Springfield, Missouri, and I am at plus 37 degrees north latitude. So 37 degrees above the horizon is my North Celestial Pole. Now, this looks like astrology, which a lot of students get mixed up with astronomy. We'll talk about this in the class. Astrology is looking at your signs and birth signs and everything, and none of it makes really any sense because it's all 3,000 years out of date. I'll show you why in a minute. But we can talk about what constellation along a path in the sky that the sun is in. So the sun and the planets and everything in the sky tends to make a line across the sky, and we call that line the ecliptic. It's the apparent path of the sun and planets and the moon across the sky. And there are about 12 or 13 constellations here that you'll recognize. You're probably one of these signs. I'm a Gemini myself, born in June. Twins, and we have those, but they're 3,000 years out of date. So here we have the tilt of the Earth. And so why do we have seasons? It's because of the tilt of the Earth, which is 23.5 degrees now, but it does vary over many thousands of years between 22 and 24 degrees. And so we have this tilt. And so in the summertime, in the northern hemisphere, we are tilted more towards the sun. Okay? And so the sun's light hits the earth more directly in the summertime in the northern hemisphere. But Australia in June is in the midst of its wintertime. We are actually closer to the sun by 3 million miles in our orbit in January, on January 3rd. Doesn't make sense, does it? You would think if you're closer to the sun, we must be a lot warmer. Well, we're so far away, we're 93 million miles away on average. So we vary between 91 and 94 million miles away from the sun. And the scenario I set up with this to demonstrate in a classroom would be if you build a bonfire and you stand 30 feet away from that bonfire and you put your hands out, and you feel that warmth, and you make 1 foot closer to that bonfire. Now you're 29 feet away. How much warmer do you feel? Is it significant? No. And so we don't really get that warming effect. It's the tilt that has the seasons. So I promised you that picture of Orion. So here's Orion the Hunter. We see this prominently in the winter sky. It's one of the biggest constellations you can find. And so we have shoulders up here, the feet down here. Orion's 3 stars makes its belt, and from the middle of the belt comes the sword, and right here, that glowing object, that's Orion's Nebula that I showed you earlier. And so Orion is very neat because it shows different colors of stars. So we have blue stars here in the belt of the Hunter of Orion. These are very hot stars, 50,000 degrees Kelvin, which is kind of a astronomer's version of the metric temperature scale that we use in astronomy. The bright red star in the belt, this is Betelgeuse. And this is a very huge star, a supergiant star, many millions of times bigger than our sun. And it's very cool, only 3,000 or 4,000 degrees Kelvin. Whereas Rigel, down here in the foot, is another supergiant, and it's bright blue. It's 50,000 degrees hot. We know that the Earth is round because we have seen lunar eclipses. And in 2018, we'll see some lunar eclipses, and I'll be sure to tell you when we'll see these. Or if we're not in 2018, if we're in 2019, and in the future, we'll tell you when they are. The lunar eclipse occurs when the moon moves in and out of the shadow of the Earth. So we have the sun, and the Earth gets in the way and casts a shadow and a cone shape out into space, and the moon goes through it. But it doesn't go dark. If you saw pictures of the total solar eclipse from August of 2017, it went dark pretty much in the path of totality. But why doesn't the moon go dark? It gets kind of red. Well, that red hue is like a sunset on the moon. It's the sun peering its light through the Earth's atmosphere and casting that red hue onto the moon like a sunset would. Very pretty. And we can actually measure how dirty or clean Earth's atmosphere is by how red that hue is on the moon. If it's very red, we have a very dirty atmosphere, lots of pollutants in the atmosphere. So here's that geometry that would need to occur for that lunar eclipse. Now, way back when, in the early Greek days, Eratosthenes measured the size of the Earth by observing the angle at which the sun's rays hit our planet's surface from two places. He made a column at the Greek site Alexandria and a well far away from that in another city, and could calculate pretty accurately the size of the Earth by the geometry of these light rays that hit those two spots. Now, I talked about this earlier. This is called precession. So the Earth wobbles on its axis like a spinning top would wobble. And so this takes about 26,000 years to occur. And because of this, the North Pole star, Polaris, like I said earlier, currently is our North Star, but not always. In about 14,000 years from now, the very bright summer star Vega will be the North Pole star. 5,000 years ago, it was this star named Thuban. And so Polaris is not always the pole star, but I guarantee you for the rest of our lives and your kids' lives and the grandkids' lives, it will be. We can detect backwards motion in the sky. And we see this with the planet Mars very nicely. And it's called retrograde motion. And so if you think of a NASCAR race, and you've got two NASCAR cars going into an embankment, into a curve, and one is in the inside track and it passes the one on the outside track. If you're looking at that car on the outside track, you go down the highway or this NASCAR track, it appears to us to go backwards. And that's the retrograde motion. As we pass Mars, which is further out in our orbit, that outside car, it will appear to go backwards for a while, and then it'll come back and it'll go back to forward motion. Very neat. Now, way back when, in the early Greeks, we had a philosopher named Ptolemy. That P is silent. Ptolemy had a very complicated system for how the universe and the solar system worked. And we have a principle called Occam's razor. You may have heard of this. The simplest idea is generally the most correct idea. And he made this very complicated. He had the Earth a little bit away from center, but close to center. We had a great big circle called the deferent, and then a planet like Mars would circle its own little orbit circle called the epicycle. And these little circles would go around and around and around the bigger circle. And that was very complicated. And it didn't quite work out. Here are those zodiac signs again. It wasn't until we had Nicholas Copernicus come along. And Copernicus was a cleric and scientist who played a leading role in becoming a modern science. And what he said was, all this time with the Greeks and into the early years of the church, was that the Earth was the center of everything, the center of the solar system, the center of the universe. And we called that geo for Earth, geocentric universe. And Copernicus said, no, that's wrong. I believe the sun, or heliocentric, helios for sun, Greek for sun, that the sun is the center and everything goes around it. And he had some help with folks named Tycho and Johannes Kepler, who worked off his work and figured this thing out, that we were not at the center of the universe. So here's the Copernican system. Wasn't quite right, but it did have the sun in the center, and that's what we go off now. And he published this. One of the things that he also said in this system would happen was that we would see phases on Venus. And Copernicus couldn't see this because we hadn't invented the telescope yet. Galileo did see this. I'll show you this in a minute. But if you take a telescope and look at the planet Venus, which is closer to the sun than we are, and look at it, you can see phases somewhat similar, not exact, but similar to what we see on the moon's phases. And that proved that Venus went around the sun and not the Earth. Very important. So here's Galileo. It's kind of weird. Some of these guys go by their first name, Galileo. Galilei, we just say Galileo. We have Tycho Brahe, we call him Tycho. Then we have Johannes Kepler come along, and we call him Kepler. Kind of weird. But Galileo, one misconception is that he invented the telescope. That's not true. It was invented the year before he made it by some Italian lens makers. But Galileo was the first to use the telescope to look up in the heavens. And it turned out Galileo was right about a bunch of stuff, and the church was not happy about this. And you will read this in the book. But Galileo was sent under house arrest. And it wasn't until 1979, we're talking about back in the 1600s, this happened. He was put under house arrest for heresy. But word spread throughout Europe of Galileo's findings, and that the moon was not perfect, and the sun was not perfect, and there were phases of Venus, and we had sunspots on the sun. Word spread throughout Europe, and books were written, and the word got out. But Galileo suffered the consequences, went under house arrest. It wasn't until 1979 that Pope John Paul II did an inquiry into the works of Galileo. And in 1992, the church said pretty much Galileo was probably right all along. We were probably wrong, but went just shy of saying exactly we were wrong and he was absolutely right. But the Vatican now has its own observatory. And here's what his telescope looked like. It was a wooden tube covered with paper and had a lens 26 millimeters, or about an inch across. And that's the end of chapters 1 and 2 for week 1. We'll see you next time.